All right, so this is the review session for EGME 541 for spring 2022, the first midterm. All right, so I looked at the poll on Canvas, and these were the top 3 choices. And so I usually only do 2, but just because this midterm I'm not going to ask you to do any frame problems. I'm just going to review frames really quickly, at least from a conceptual perspective of what you should know. Then I'm going to jump into beam and 2D truss equations. I think those you're definitely going to have some problems on those. Okay, so let's start with frame equations. So this was the last topic that we covered, right before the midterm. Okay. And so frames, remember, conceptually, they are elements that can exhibit all different kinds of deformation. Okay, so there's basically no assumptions on the on the deformations for frames because they can capture all of them. Okay. And so the types of deformations that we have, let me go ahead and draw the element here. Right. So of course we have axial deformation. Right. So axial deformation refers to compression and tension. We have transverse deformation, and so that's deformation that's perpendicular to the to the element. And we also have rotations, or in other words, changes in orientation. Okay. So frames can exhibit all 3 of these things, and so that's why it's the most general element. And so and for a lot of reasons, people say that frames are probably the only element that you should be using in these kinds of problems. But because it's so general, it's also the most complex to solve. Okay. And so I think at this point everyone's familiar with it because probably everyone's working on the homework. But the reason the reason I think these problems are difficult is not because conceptually they're difficult to understand or the process is difficult to follow. It's just the raw amount of calculations that you have to do is just kind of crazy for these ones. And that's best illustrated by its element stiffness matrix. And so I'm not going to write the element stiffness matrix because I only have about an hour. And so I think that's going to take up too much time, but I think everyone's familiar with it at this point. Okay. Okay. And so what I do, and so I don't want to do any frame problems because that would take up the entirety of this review session. But I did want to talk very briefly about how we obtained this element stiffness matrix, because how we obtained it was really interesting. Okay. Right. And so we mechanically went through the process of deriving this in class, but I think it's worth talking about kind of just from a conceptual point of view what it represents. Okay. And so chronologically speaking, we started talking about frames after we had talked about trusses and beams, right? And so trusses are elements that have axial deformation, and beams have the transverse deformation as well as the rotation. Okay. Okay. Right. And so one way that you can look at frames is just simply just the combination of these two together. Okay. And if you look at our notes about how we derive the frame element stiffness matrix, what you'll see is that we literally just took the element stiffness matrix for a truss, the element stiffness matrix for a beam, okay, put them both into the stationary coordinates along with the same, and we put them in the augmented forms, with all the additional degrees of freedom that we need, and then we just kind of put them on top of each other, okay? Okay. And so on the one hand, we have the truss element stiffness. Okay, in the stationary coordinates. Okay, and then we have the beam element stiffness matrix and in the stationary coordinates. Right. We had to derive this, and so we didn't actually go over the beam element stiffness matrix and stationary coordinates, in the beam unit, because we were focusing just on the local coordinates. And so the first thing we did was we applied our transformation matrix to the beam element stiffness matrix. But once we had both of these, all we did was simply just put them on top of each other, and just in true finite element format, whenever we had elements that overlapped or entries that overlapped, we just added their values together. Okay. Okay. So that's all it is. And so, there wasn't any new theory for frames. There wasn't any new equations for frames, because we had already developed all of them in the truss and the beam units. And so all we had to do was just kind of combine them together within a single framework, right? And so I think the most difficult part of this was taking our beam element stiffness matrix and then transforming it into the stationary coordinates, because we had never done that before. And so, once you got that, then this becomes clear. And so look at our derivation again. And then look at the final element stiffness matrix for the frame. You'll see that there are a lot of terms that are just kind of the sum of two things, right? We have the one thing added to another thing, right? In those cases, when you have one thing added to another, you can clearly see that one part of that sum comes directly from the truss equations, and then the other part of that sum comes directly from the beams. Okay, let me show you one example of this, just because I'm not going to write the whole thing, but let me show you kind of the top leftmost element. Okay, and so the top leftmost element is AC squared plus 12I over L squared times S squared. Okay, and so this term right here, because it has the cross-sectional area, remember beams didn't have any term with the cross-sectional area. This comes directly from the truss equations. Okay. Whereas this term right here, the I indicates that this is from the beam equation, right? Because the truss equations do not make use of the moment of inertia at all. Right? And so this quantity right here is in the top left, or in the 1-1 slot of the frame element stiffness matrix. Okay. And so you can see in that slot, where we have the sum of these two terms, one of them clearly comes from the truss equations, while the other one clearly comes from the beam equations. Okay. And so there's no mixing. And so if you look at all the terms in our elements, in the element stiffness matrix of the frame, there's no terms we have A multiplied by I or something like that, right? Because A is clearly from the truss, and I is clearly from the beams. And so there's no multiplication mixing, right? So the only mixing that occurs is purely through addition. And that addition is a result of these two element stiffness matrices being combined together. Okay. and so, we went through that process, mechanically. And so we derived it, and so we went through all the details of it. But I wanted to make sure and kind of step back and talk about, what the purpose of all that was, and to kind of look at it from a different perspective, because I think that's something that's really important. Okay. Okay, and so that's all that I want to talk about frames. And so remember, frames, there's not going to be any frame problems on the exam, but you should understand what frames are from a conceptual standpoint. Okay. Okay, so now let's go over beams. Okay. And so it kind of seems like we're going backwards, because we just talked about frames that have beam deformations, but now we're talking about beams themselves. Okay, and so beams are structural elements that exhibit transverse deformation as well as rotations. So here's our beam structural element, okay? So our transverse deformations are deformations that are perpendicular to the long axis of the element. And rotations are just like that, okay? Okay. And so that's what beams are. So beams don't change in length, and so they don't expand or compress. But they can, bend, okay? All right, and so the element stiffness matrix for a beam is given by the following. Okay. And so it is a 2x2 matrix, or excuse me, a 4x4 matrix. Okay. So we have an EI over L cubed out in front. And our degrees of freedom are, again, our transverse displacements and our rotations, okay? All right, so let me go ahead and write out the rest of the equations here. Okay. And of course, this is the one that you have to derive in the homework. Right, and so our element stiffness matrix looks like the following. Okay. Okay, and so at this point, it's a good time to review, review our finite element solving process. Okay, and I think this will be a good chance for you guys to get an idea of kind of the scale and the scope of the problems that I'm going to ask you on the midterm. Okay, and so let's review the finite element solving process, and then let's go ahead and do an example where I'll show you kind of, it's a good chance to kind of see what the complexity is going to be like. Okay? And so the finite element solution process, I think, is one of the most important topics for this class, because we're literally going to apply it for basically every single problem. It's just, the specific details of the certain steps are going to change, you know, depending on the method and the elements involved, specifically with the element stiffness matrix. But the idea and the process of going through this is exactly the same. And in fact, you saw it as well. So when we were working on our code, you know, on Wednesday of the past week, you know, we followed the exact same process in the code. And so this algorithm is not just unique to just hand problems. You know, anything that implements the finite element method, you know, codes and all that stuff follow the same methodology. Right, and of course, step one, I guess maybe we should call it step zero. Step zero is to, you know, identify the problem, identify the geometry, and identify all the problem parameters. Okay. And so I know that that might seem obvious, you know, especially for problems that I'm giving you, but you know, it's important to note because you know, a lot of times it's not exactly clear. All right, number two is to you know, write out the element stiffness matrices for all the elements. Okay. And so this is assuming that the mesh or the discretization is given to you, right? And so you know, this is strictly just for textbook problems then. Because if you had a real life geometry, you know, how you mesh the geometry is going to be more or less up to you. Okay. But for these problems, you know, just because I want everyone to kind of work on the same thing and get the same answer, you know, the discretization or the mesh, or you know, how many elements you have is going to be given to you. Okay. Number three. So number three is assembly. Okay. And so assembly, remember what that means is to take all the element stiffness matrices and put them into a single global linear system. Okay. Let me continue this on the next line. Okay. All right. Number four. Once you have the global linear system, you're going to need to apply boundary conditions onto it. Okay. And so the boundary conditions, those are going to be all your loads, all your constraints. Okay. And so wherever they're located in your geometry, you have to apply them here onto the global system. Otherwise, you can't solve. Right. Step five is to actually solve the system. And so after you apply the boundary conditions, you're going to have a linear system that you can actually solve. Okay. And so you can actually plug that matrix into MATLAB and solve it. Right. And step six is to post-process and analyze. And so once you have your primary solution, you can use that primary solution to compute a lot of derived quantities. And so things like the stress in the elements, things like the reaction forces on at the supports. Okay. And so that can only be done after you solve the finite element solution. Okay. Okay. And so of course, on an exam where you're not going to have access to MATLAB or any kind of heavy computing device, there's a lot of limitations of what I can ask you. Okay. And so, you know, you're only going to be responsible for the parts that I've just boxed right here. Okay. And so you're going to need to be able to, you know, identify the geometry and the parameters. You have to be able to compute the element stiffness matrices. You have to assemble it, and you have to apply boundary conditions. Okay. And so that's all that I'm going to expect from you. And actually, all three problem solving questions on the exam follow this, follow this exactly. They're all exactly the same. Okay, and so I'm not going to ask you to compute stresses or anything because that depends on the finite element solution, which you're not going to be able to obtain, without MATLAB or computer. Okay. Okay, so let's go ahead and do an example. And so the example that I'm going to pick is actually from the homework because we've actually seen the in-class examples already, but I'm going to change the numbers around so that it becomes nice. Okay, and so on the exam, what you'll notice is that I'm going to give you these finite element problems, but I've set the problem parameters very deliberately so that you don't have to spend a lot of time doing a bunch of calculations and copying numbers. Especially for irrational decimals, which can sometimes happen in these cases. And so, I don't want you to waste your time doing that on the exam. And so I made it so that the numbers are really, really reasonable. Okay. Okay. And so to that end, let's go ahead and let's do problem 2B on the latest homework. But I'm going to modify it a bit just to save a bit of time. Okay. I like this one because it has a combination of beams as well as a spring. Okay. All right, and so we have a wall here, okay? And we have 3 beams in a row. Okay, and so they're all connected end to end. And so this is node 1, this is node 2, this is node 3, this is node 4. Okay, this is element A, element B, element C. Okay, but in addition to that, we also have a spring hanging from the ceiling that's also attached to node 4 right here. Okay, so this is node 5. This is element D. Okay, and element D has a spring constant of K. Okay. Okay, so let's go ahead and specify the numbers. And so again, I'm going to kind of set these so that they make the calculation a little bit easier. Okay. And so let's say that the lengths of all the elements are the same. Okay, and so the lengths of all the elements, let's say that they're all 1 meter. Okay. The Young's modulus, let's say that it is 200 megapascal. Or let's just do 20 megapascal. Okay. Okay, let's say that the moment of inertia, not the area. Let's say the moment of inertia is 0.05 meters to the 4th. Okay. Oops. I spit on my screen a little bit. Okay. And then for the spring constant, let's say that this is equal to 2 meganewtons per meter. Okay. And we have our mode P. Okay. And let's say P here has a magnitude of 100 kilonewtons. Okay. Okay. And so this problem, we're going to solve it as if it were an exam problem. So we're going to need to compute. We're going to compute all the element stiffness matrices. Okay. Then we're going to assemble and apply boundary conditions. Okay. All right, and so here's our problem. And so the the parameters here I've chosen so just so that it'll make it easy. And so first thing, let's compute all the element stiffness matrices for the beams because they're all identical, right? So let's compute the factor in front, right? So if we look at our beam element stiffness matrix, we have this EI over L cubed out in front. So let's go ahead and just compute that straight up, just so we don't have to worry about it. Okay. Right, and so we can see here that this is 20 times 10 to the 6 Pascal. Okay. I here is 0.05. Okay. And then we're going to divide by 1 meter cubed. Okay, and so if we perform this, 0.05 is the same thing as 1 over 20, right? And so we have 20 times 10 to the 6 times 1 over 20. And so this EI over L cubed is simply just going to be 10 to the 6 because we have 1 cubed on the bottom and 1 cubed is still just 1, okay? Okay, and so with that in mind, let's go ahead and start assembling, okay? And let's start with element A. And so element A here is connected to nodes 1 and 2. And so we have F1y, M1, F2y, M2. Okay. We have our EI over L factor, EI over L cubed factor, so that's 10 to the 6th. Okay. And then we're going to multiply it by our element stiffness matrix. Okay. And so our element stiffness matrix here is going to be 12. And then we have 6 times the length, and so that's just going to be 6 because our length here is just 1, right? And then we have a minus 12, and then another 6, okay? And this is equal to U1y, theta 1, U2y, theta 2, okay? Or excuse me, that's the solution vector on this node, okay? Next, we have the next line, and so we have 6L, and so we have 6L is just a 6. Actually, let me do what we usually do. Let me go ahead and write, now that we've written the first row, let me go ahead and write this into the column. Okay, so we have 6 minus 12 and 6, right? Next, we're starting the second row. So we have 4L squared. 4L squared is just 4. Then we have minus 6L. And so since L is 1, that's just going to be minus 6. Okay. Then we have a 2L squared here. And so 2L squared is just going to be 2. And again, I'm going to write this into the corresponding column. Right. Next, we have a 12 on the diagonal, and so that just stays 12. And we have minus 6L, and so that's just going to be minus 6. And then in the bottom right, we just have a 4. Okay, and so since all 3 beam elements here are identical, and so I'm going to just just kind of copy their values down. Right, so element B, the only thing that's going to change in between elements A, B, and C is the nodes that they're connected to. Okay, so that's element B, mathematically identical to element A. It's just they're acting on different nodes. Okay. Right. Next, we have element C. So element C is the same. It's just the nodes are different. And so element C here acts on nodes 3 and 4. And so we have F3y, M3, F4y, M4. Okay. This is 10 to the 6. This is going to be equal to the same thing. So 12, 6, minus 12, 6, 6, minus 12, 6, 4, minus 6, 2, minus 6, 2, 12, minus 6, minus 6, 4. Okay. All right, so those are all the beam element stiffness matrices. So that looks good. Okay. Now let's go to the spring. Okay, and so for the spring element stiffness matrix, you can see here is connected to nodes 4 and 5. But remember, springs can't rotate, and so the spring is not going to contribute anything to the rotational degree of freedom of the beams. Okay, and so the only thing that the spring is going to contribute to is just the two Cartesian deformations there. Okay, and so those Cartesian deformations are F3y, F4y, or excuse me, F4y, F5y. Okay. Then we have the spring constant. And so the spring constant is 2 meganewtons per meter. Okay. And so just to keep things consistent, I'm going to keep a 10 to the 6 power in front. And we have a 2 minus 2 minus 2, 2. And then we have U4y, U5y. Okay, so that's all the element stiffness matrices. So all that looks good. And so next is the assembly and boundary conditions. Okay. All right, and so for the exam, because you are going to be so limited on time, I'm going to let you guys do these 2 steps kind of at the same time, right? Because for a lot of these problems, you can look at the domain kind of just really simply and say that I'm going to have fixed supports at these locations. Okay, and so just to save yourself some time from having to write in the element stiffness matrices in those rows, you can just go ahead and write them in directly. Okay, but before we do that, we have to actually make space for everything. And so for this system, since we have 4 nodes that have beam deformations and 1 node that has a spring deformation, we're going to have 9 degrees of freedom overall. And so we have a 9 by 9 matrix. So we have an F1y, M1, F2y, M2, F3y, M3, F4y, M4, and F5y. Okay. Okay. I'm going to put a 10 to the 6 out in front just to, make it so that we're only plugging in just integers, just to save us a bit of writing. Okay. So let me go ahead and write in the, the entries here. So we have a U1y, theta 1, U2y, theta 2, U3y, theta 3, U4y, theta 4, okay. U5y, right? And so here we have a U1y, theta 1, U2y, theta 2, U3y, theta 3, U4y, theta 4, and U5y. Okay, and so since we already know what the boundary conditions on this look like, right? Since we know nodes 1 and 5 are fixed, okay, let's go ahead and apply this right away. So node 1 is completely fixed, and so that means U1y and theta 1 are both going to be equal to 0. And so we have a 1, 0, 0, 0, 0, 0, 0, 0, 0. And then a 0, 1, 0, 0, 0, 0, 0, 0, 0. Okay. And of course, that means the entries in the forcing vector are also going to be 0. Okay. And that enforces the fixed constraint at node number 1. Right. And then we have a fixed constraint at node 5. So node 5 is 0, 0, 0, 0, 0, 0, 0, 0, 1. And of course, this one right here also is 0. Okay. All right. And so in fact, we can also apply the mode. And so the mode we know is acting downwards. We only have 1 mode here acting on node 4. Okay. And so that means F4y is equal to minus P. Okay. Where, what did we say P was? P was 100 kilonewtons. Okay. So let's go ahead and replace that here. Okay. And we'll use a different color here just to kind of illustrate that. Okay. And so we have minus 100 E3 on U4Y. Okay. And then every other node, since they have no loads being applied and no supports there, they're also all going to be 0. Okay. Okay, so that saves us a bit of work because otherwise we'd have to kind of plug everything in, put all the numbers in, and then just having to erase it anyway for the for the constraints. So we just kind of did that before. Okay, so now the next step is assembly. And so I'm going to use the same method that I usually use in class, where I box out the areas where we're going to plug these in. Okay, so let's start with element A. Right, so element A acts on nodes 1 and 2, and so it's going to be acting on these nodes right here. Okay, so that's element A. Next, we have element B. Okay. Element B is on nodes 2 and 3, and so let's go ahead and draw those out. Okay. All right, next we have element C. Okay, element C is nodes 3 and 4. Not all the way there. Okay. And then node D, I'm going to use orange or element D. Element D is a spring, and so the spring is only going to be acting on the U4Y and U5Y. Okay. And so that's going to be, let's see, that's going to be this one right here. Okay, it's going to be this one right here, and this one right here, and this one right here. Okay. And so, of course, the bottom two we're not going to add together because that's just that's just part of the constraint. But it's important still to know where where it goes. Same thing for element A too. So element A, even though it's intersecting with the constraint, I still want to box it out just to let me know where it's going to be. Okay, so now let's go ahead and add the element stiffness matrices here. So luckily they're all the same, and so we can just add these together simply. Okay, we have minus 12 here, minus 6, 6, and 2. Okay, right? Yep. Okay, so that's the bottom left of the element stiffness matrix. Then we have the overlap part, and so we have the overlap of the bottom right of element A and the top left of element B. Okay. And so we add those together. Okay, all the overlap parts I'm going to write in red. Okay, so all the overlap parts you can see here, we have a 24. Right, so that's 12 plus 4, 12 plus 12. Then we have a 6 minus 6, which is 0. Another 6 minus 6, which is 0. And then a 4 plus 4, which is 8. Okay. Okay, from there we have the other off parts which don't overlap, and so I'm going to write these in green. Then we have some more overlap parts, and so the overlap parts are going to look the same as up there. So we have a 24, we have a 0, we have a 0, we have an 8. Okay. Right. And then we have an overlap of the spring together with the element C. Okay. Be very careful about where you put the spring because it could be a bit tricky. Okay. And so if you look kind of carefully at the at the structure of this stiffness matrix, you could see that the spring is going to overlap on that entry right there, okay, that 12. And so on that one entry, we're going to have a 12 plus a 2, and so that's going to be a 14, right? And then everything else is going to have, their usual values, okay? So we have a minus 6, or excuse me, minus 12, minus 12, 6, minus 6, 2, and then minus 12, minus 6, 6, 2, and we have minus 6, minus 6, 4. Okay. And then finally, we have one more entry for the spring, which is this little box guy on the right. And so, of course, this guy is 2. Okay. And then everywhere else that does not have a box, we're just going to fill them in with zeros. Okay. All right, and so that's as far as I would expect you to. I'd expect you to take it for the exam. Okay, And so if you could get it to this point, and the numbers are going to be nice and gentle so that you can, you can actually plug these in, and it's not that much arithmetic. Hopefully, what I'm hoping for is that you can do a lot of the calculations in your head, because I think, looking at people do these kinds of exams before, I think people, they use a lot of their time kind of punching numbers in the calculator and copying them over. And so I wanted to make the math or the arithmetic simple enough that you can do them in your head, so you could focus on just the finite elements parts, which is, computing the element stiffness matrices and then putting them in the right places in the global system. Okay? And so that's what I'm going to be mostly grading you on, is those things. Okay. And so that took a bit longer than I thought. And so I think I only have time just to go over trusses in name. Okay. But hopefully that one example there gave you a good indication for, the types and level of the problem that I'm going to give you on the exam. Okay. Right. And so the next thing that we're going to look at is truss equations, specifically the 2D truss equations. Okay. All right, so the 2D truss equations, these refer to truss elements that are oriented arbitrarily, okay? Okay. And so by arbitrarily, what I mean is that we can describe its orientation using some kind of rotation angle. All right, and so the arbitrary truss element looks something like this. Okay. Where we have the angle theta right here, and so theta here is the orientation angle. And so remember, the way that you measure the orientation angle, it's always relative to the positive x-axis. Okay. Okay. Right. And so remember the convention that we had before. So the convention was that we drew an arrow from the lower numbered node on the element to the higher numbered node. Okay. Okay. Then to describe the orientation angle, we think about, if we have a vector that's pointed this way, how much would we have to rotate counterclockwise from the positive x-axis to get to that orientation? Okay. Okay. And so for instance, let's say that we had an element that looked like this, right? Okay. So let's say that this is node 1, this is node 2, okay? And so, we draw a vector that goes like that, right? And so the orientation angle, or the one that we plug into our element stiffness matrix, the way that we obtain that was we first draw our positive x-axis, and then we try to rotate around there as much as we need to. Okay, and this angle of rotation that I have here, this is the theta angle that you would plug into the element stiffness matrix. Okay. Okay. And so that's how we describe the orientation of the truss elements. Okay. Next thing is how we obtain the element stiffness matrix itself. Okay. So let me just go over I'm not going to expect you to redo the derivation, but just to kind of review the steps of how we got this. Okay. And so remember, to obtain the element stiffness matrix, we took our element stiffness matrix and the local coordinates. Okay. Actually, no, let me not put numbers on that. Let's just say that we took where, if you remember, the element stiffness matrix and the local coordinates look something like this. Okay. Okay, so it's simply just a 2x2 matrix. Okay. Right, and then what we did was we applied our transformation matrix to this guy. And in fact, what we did was we took this element stiffness matrix and we pre-multiplied, or in other words, we multiplied before by the transformation matrix, and then we post-multiplied as well. Okay. So I believe it was, which one was transpose? I think this one's transpose. Yeah. And so we made a transformation sandwich. Okay. Right, and so all the sines and cosines that you see in the element stiffness matrix for 2D truss, they come from these transformation matrices. Okay. All right, and so if we follow that process, we end up with the following element stiffness matrix. Okay, and so our element stiffness matrix in the stationary coordinates, which again is a 4x4. So we have an F1x, F1y, F2x, F2y. Okay, this is equal to AE over L multiplied by cosine squared, cosine sine, minus cosine squared, minus cosine sine. Okay. Okay, this is U1x, U1y, y, U2x, U2y. Okay. Then we have a sine squared. We have a minus cosine sine. We have a minus sine squared, cosine squared, cosine sine, sine squared. Okay. And of course, this whole thing is symmetric, right? And so, for our symmetric matrices, remember what we do is we take, as soon as we write a row, we write it into the column. Okay. And so let me go ahead and give you the full version of this. So I think in the notes, I just give you the symmetric version. Okay. And so if we write these terms in, we have a cosine sine there. We have minus cosine squared, minus cosine sine, minus cosine sine, minus sine squared, and a cosine sine. Okay. And so this is the element stiffness matrix. of a 2D. Okay. All right. And so from there, now that you have this element stiffness matrix and you kind of understand where it came from, now is the time where you would have to do some problems, okay? But the problem solving process follows exactly the same as our beam, that we talked about earlier, okay? So first you're going to examine the problem, you're going to identify all the elements and their properties. Next, you're going to write out their element stiffness matrices. Third, you're going to assemble, and then you're going to apply boundary conditions, and then that's where you would stop, for the exam. Okay, I will say that I think the thing that makes these problems really hairy is that first of all, if the parameters of the problem are not nice, right, and so they require a lot of decimal points to to make work, then it's going to be a lot of writing, a lot of copying. And so but the other thing that can happen for these types of problems is that you have sine or cosine terms that are kind of nasty, okay? And so even if you have sine or cosine of 30 or 60 degrees, like that can be a little bit difficult just because one of those is like √3/2, the other one is just 1/2, and so you're dealing with irrational numbers because you have a square root of 3. And so I will say for the exam, there is a 2D truss problem, just like we talked about at the end of class on Wednesday. There is a 2D truss problem, but the only angles that I will give you the only angles that I'm going to give you on the exam are going to be either 0 degrees, 90 degrees, 45 degrees, or any multiple of these. And so it could be something like 180 degrees, 270 degrees, right? So those are all the multiples of 90. We can also have 135 degrees. What's next? 225 degrees, and also 315 degrees. And so those are the only angles that you can expect to have on the exam. And the reason I picked those is because when you compute the sines and cosine of those angles and you square them, you end up with with rational numbers. And so you end up with either 1, 0, or -1, or 1/2, or -1/2. Okay. And so I think those are reasonable to do, for the exam. Now, remember what I said earlier. My goal for the computations portion of this exam is to make it so that you can compute a lot of the quantities by head. And so you focus just either on the writing or you focus on the finite element methodology. Okay. And so I don't want the computation. I don't want just calculations on your calculator to be the bottleneck on the exam. Okay, and so I think that's all that I have to say about trusses and beams and frames. Okay, and so the rest of it is just going to be practice. And so make sure you're doing practice problems. Make sure you redo the homeworks. If it helps, one thing that you can do the same thing that I did for this example up here. Where I took a problem that we've already done on the homework, but I just changed the numbers up. And so I think that's a good way to kind of inject some new life into an old problem. Where maybe you've kind of gotten used to the numbers, you've gotten used to the solution already. If you change up the numbers a bit, then it'll be kind of almost like a whole new problem. Not exactly, but it'll at least put your mind through the process of practicing the methods. Which is what you should aim to do when you're studying. Okay, and in fact, what you can do is you can change the numbers so that the calculations are they're easier to compute than the original ones. Okay? And so that'll give you some really good practice for the exam. Okay, and so that's it for the review session. And so if you have any other questions on anything, please don't hesitate to reach out. I'm going to try to be as available as I can up until the exam. And so if you have questions, just email me, and then I'll try to help you the best I can. All right, so have a great weekend, everyone. Best of luck studying, and I will see you next week.